Welcome to AI Frontiers. Today we're diving into an exciting array of papers from computer science, learning, or cs.LG. This field is pivotal in driving advancements across numerous domains, from healthcare to autonomous systems, by enabling computers to learn from data and make intelligent decisions. In this episode, we'll explore an exciting array of AI research papers, delve into dominant research themes, examine key findings and methodologies, highlight seminal papers, and discuss future directions and ethical considerations. Computer science learning, or cs.LG, is a vibrant subfield of computer science focused on developing algorithms and models that allow machines to learn from data. This includes everything from supervised learning, where models are trained on labeled data, to unsupervised learning, where patterns are discovered in unlabeled data. Recent advancements in deep learning, reinforcement learning, and federated learning have pushed the boundaries of what's possible, making cs.LG a cornerstone of modern AI research. Applications span healthcare, autonomous systems, and more, driving innovations across various domains. One of the most pressing concerns in the field is ensuring the stability and robustness of neural networks, particularly in the face of adversarial attacks and data perturbations. Researchers like Ming Zhang et al. Are tackling this issue head-on, proposing novel formulations to analyze model stability under graph topology perturbations. Their work is crucial for applications where reliability is paramount, such as autonomous vehicles and medical diagnostics. Another hot topic is temporal modeling and forecasting. As our world becomes more interconnected, the ability to predict future events accurately is increasingly valuable. Minglin Kong et al. Are at the forefront of this research, introducing a data-driven time-embedding method using dynamic mode decomposition to capture complex multiscale periodicity in spatiotemporal data. Think of it like predicting traffic patterns in a bustling city. Understanding the ebb and flow of vehicles over time can help optimize routes and reduce congestion. Federated learning is another area gaining traction. This approach allows models to be trained across multiple decentralized devices without exchanging data, addressing privacy concerns and data silos. But it's not without challenges, particularly data heterogeneity and communication efficiency. Papers by Divyansh Junjunwala et al. And Xiao Zhao are making strides in this area, proposing methods to enhance federated learning's performance and robustness. Explainable AI, or XAI, is another critical theme. As AI systems become more integrated into our daily lives, there's a growing need to make these models more interpretable. Junrui Li et al. Are leading the charge with XAI units, a benchmark for evaluating feature attribution methods. Meanwhile, Yavuz Bachman et al. Are examining the challenges of deploying uncertainty estimation methods in real-world settings, ensuring that AI decisions are not only accurate but also understandable. Generative models and synthetic data are being explored for various applications. These models can create new data instances, which is invaluable for training and testing AI systems. Yuzuo Zhang et al. Are using reinforcement learning to generalize from synthetic graph data to real-world tasks, while Jacob K. Christopher et al. Are introducing neurosymbolic diffusion for generating physically grounded outputs. This research is paving the way for more robust and adaptable AI systems. Several common techniques emerge from the papers, each with its strengths and limitations. Graph convolutional neural networks, or GCNNs, are powerful tools for analyzing graph-structured data, but face challenges in stability and robustness. Techniques like those proposed by Ning Zhang et al. Aim to address these issues by analyzing model stability under perturbations. Dynamic mode decomposition, or DMD, is a data-driven method for extracting temporal modes from observed data, useful in spatiotemporal forecasting. Its strength lies in capturing complex multi-scale periodicity, but it requires careful integration into deep learning models. Federated learning with low-rank adaptation, or LoRA, is a parameter-efficient fine-tuning method for large language models, reducing communication and computation costs. However, data heterogeneity remains a challenge, which methods like FedRPCA aim to address. Reinforcement learning from human feedback, or RLHF, is a technique for aligning large language models with human preferences. Erhan Xu et al. Introduce a doubly robust preference optimization algorithm that remains consistent even when the preference model or reference policy is misspecified. Neurosymbolic diffusion models combine the generative capabilities of diffusion models with symbolic optimization, ensuring compliance with physical and structural constraints. This approach enhances the applicability of generative models in critical applications but requires careful design and integration. First up is On the Stability of Graph Convolutional Neural Networks, a Probabilistic Perspective by Ningxian et al. The researchers set out to understand the stability of graph convolutional neural networks, or GCNNs, under perturbations in the graph topology. Traditional stability analyses focus on worst-case perturbations, but this paper introduces a probabilistic perspective to characterize output perturbations across a broad range of input data. The findings are compelling. The authors demonstrate that their probabilistic perspective provides a more accurate and practical assessment of GCNN stability. Extensive experiments validate their theoretical findings, showing improved representation stability and robustness against adversarial attacks. This work highlights the importance of incorporating data distribution into stability analysis, offering a new direction for enhancing the robustness and trustworthiness of GCNNs in real-world applications. Next, let's explore dynamic modes as time representation for spatiotemporal forecasting by Menglin Khan et al. This paper aims to improve spatiotemporal forecasting by introducing a data-driven time embedding method that captures complex multiscale periodicity in the data. The authors employed dynamic mode decomposition, or DMD, to extract temporal modes directly from observed data, which are then integrated into deep spatiotemporal forecasting models. Picture this. You're trying to predict the weather for the next week. Traditional methods might look at past weather patterns at fixed intervals, but DMD allows for a more nuanced understanding of how weather systems evolve over time. The authors show that the DMD-based embedding improves long-horizon forecasting accuracy, reduces residual correlation, and enhances temporal generalization. This work provides a lightweight, model-agnostic, and effective solution for capturing temporal dynamics in spatiotemporal data, advancing the field of time series forecasting. Finally, let's delve into FedRPCA, enhancing federated LoRa aggregation, using robust PCA by Divinciu Junwala et al. The authors aim to address the challenges of data heterogeneity in federated learning by improving the aggregation strategy for LoRa-based fine-tuning. They introduce FedRPCA, a method that decomposes client LoRa updates into a common low-rank component and client-specific sparse components using robust principal component analysis, or robust PCA. This approach consolidates common knowledge and amplifies client-specific knowledge. Experiments across various vision and language tasks demonstrate that FedRPCA achieves higher final accuracy and faster convergence compared to competing baselines. This work provides a practical solution for enhancing the performance of federated learning in the face of data heterogeneity, making it more applicable in real-world settings. Looking ahead, the future of cs.LG is bright. Researchers are increasingly focusing on developing more robust and interpretable models, integrating diverse data sources, and applying AI to new domains. The intersection of AI with other fields such as healthcare, finance, and environmental science promises to yield innovative solutions to complex problems. But there are challenges ahead. Ensuring the robustness of AI systems in the face of adversarial attacks and data perturbations remains a critical concern. Federated learning, while promising, still faces hurdles in data heterogeneity and communication efficiency, and as AI becomes more integrated into our lives, the need for explainable and interpretable models will only grow.